conjugate. What are the properties of conjugate? Properties. First property is that the conjugate of a conjugate will give you the same complex number. Okay, all these properties can be proved. You can go through the proofs. The proofs have not come directly yet, and I don't think it will come. The next important property is that if z is equal to z bar, if a complex number is the same as its conjugate, then we say that this complex number z is real, is a real number. That is, we say that the imaginary part of z is 0. Okay, this is the second property. The third property here is that the sum of the conjugate of the sum must be equal to the sum of the conjugates. That is the next property of the conjugate. And similarly, for the same follows with subtraction also. That is z1 minus z2 whole bar is equal to z1 bar minus z2 bar. Okay. Fifth property is that you can, in fact, these two laws you can extend for any number of complex numbers. Extension is that z1 plus z2 for any number of complex numbers conjugate of this sum will be the sum of the conjugates for any number of complex numbers. You can extend this property. Okay, similarly we have z1 z2 bar, that is the product, the conjugate of the product is equal to product of the conjugates. Okay, the extension here is you can extend this for any number of complex numbers. Okay, any number of complex numbers. Once we have dealt with the sum and the product, we now come to the quotient. Z1 by Z2 whole bar, that is the quotient, the conjugate of the quotient is equal to quotient of the conjugates. Okay, so Z1 by Z2 bar must be equal to Z1 bar by Z2 bar. Okay, and next, again, a very important property is that the square of a conjugate number, square of a complex conjugate number is equal to the conjugate of the square. Okay, so let's write this way: if you square a conjugate number, it will be the same as the squaring of the number and finding its conjugate. Okay, that is what it means. These are the properties of conjugates. Now, moving to some of the problems here. No, okay, one more concept is left, that of multiplicative inverse. Multiplicative inverse. Okay, the multiplicative inverse of a complex number z is its reciprocal. Okay, so whatever complex number is given, if you want to find out its multiplicative inverse, you just take the reciprocal of that complex number. Okay. So now we move on to the problem with these concepts. The question here is, let us do one problem from here. Okay, this one, say 3, 4. Find the conjugate and reciprocal of the complex number. So what I write is, let z is equal to root minus 1 minus 3. You need to find out the reciprocal, conjugate and the reciprocal. You can write this as I minus 3. Okay, or you can write this as minus 3 plus I, writing the real part first. Okay, so what should be the conjugate of this? You simply change the sign of the imaginary part. This is your conjugate. Next question comes reciprocal. Reciprocal of z is 1 by z. And what is 1 by z? 1 by minus 3 plus I. But the question is, we need to write this in the form, in such a form that the real part is separate and the imaginary part is separate. So what you do is you multiply numerator and denominator by minus 3 minus I. Okay, so you get minus 3 minus I by minus 3 square minus I square. You get minus 3 minus I by 9 minus of minus 1. You get minus 3 minus I by 10. So you get minus 3 by 10 minus I by 10. Or you can write this as minus 3 by 10 minus 1 by 10 I. Okay, so this is the reciprocal of this complex number, of the given complex number, this one. Okay. Fine. So this is one. The next problem that I'm going to work out is multiplicative inverse. Look at number 7. Find the multiplicative inverse of the following complex numbers if it exists. If it exists means, see, I told you that for a complex number z, multiplicative inverse is one by z, where z cannot be equal to 0. Z is not a zero complex number, or you can write this as 0 plus 0 I. Understood? So only if z is a non-zero, then only you will be able to find its multiplicative inverse. That is why they have said if it exists. Okay. So let us work out this 8, 7. So we start by saying let z is equal to 3 plus 4i by 4 minus 5i. 3 plus 4i, multiply the numerator and the denominator by 4 plus 5i. Because we want to write this complex number in the form e plus ib or x plus iy, so that the real part is separate, the imaginary part is separate. Multiply the numerator, normal multiplication, 4 into 3, 12 plus 15i plus 16i minus plus 20i square. And in the denominator you will get 4 square minus 5i whole square. So this is 12 plus 31i minus 20 divided by 16 minus 25i square. So this is 12 minus 20 is minus 8 plus 31i divided by, this is 16 plus 25, which is 41. You get minus 8 by 41 plus 31 by 41i. Okay. This is, we have written in the form a plus ib. Okay. You need to find the multiplicative inverse. Okay. For multiplicative inverse, I've made a mistake here. For multiplicative inverse, you don't need to find, you don't need to write it in the form a plus ib. What you simply do is you take the reciprocal. Multiplicative inverse of z is 1 by z. What is 1 by z? 1 by 3 plus 4i divided by 4 minus 5i, which can be written as 4 minus 5i divided by 3 plus 4. Now you can write this in the form a plus ib by the same usual technique. You multiply the numerator and denominator by 3 minus 4i to get a plus b into a minus b in the denominator, and then you get 12 minus 16i minus 15i plus 20i square divided by 9 minus 16i square. This actually comes to 25 in the denominator. And the numerator, what you get? This 20i square is nothing but minus 20. 12 minus 20 is minus 8 minus 31i divided by 25. So you simply get minus 8 by 25 minus 31 by 25 times I. This is what your multiplicative inverse of z is. Okay, is that absolutely clear? Twelve two. Perform the indicated operation and give your answer in the form x plus iy, where x and y are real numbers. Okay, you simply need to write this in the form x plus iy. Let us say z is equal to, write this as 1 minus root minus 16. So you get here, you get 2 minus, you can write root minus 25 as root minus 1 into root 25 divided by 1 minus root minus 1 into root 16. And root minus 1 you can write as I, and root 25 is 5. 1, and again root minus 1 you can write this as I, and root 16 you can write as 4. Now you multiply. Because we want to write it in the form a plus ib or x plus iy, that is why we multiply the numerator and denominator by 1 plus 4i. So this is 2 plus 8i minus 5i minus 20i square divided by 1 square minus 4i whole square. So this becomes 2. 8i minus 5i is 3i, and this becomes divided by 1 minus 16i square. So this becomes 22 plus 3i divided by 17. So this becomes 22 by 17 plus 3 by 17 times I. So this has been written in the form x plus I y. Okay. Let's move on to the next one. Express this in the form a plus ib. Number 15. Number 15. You want to express this in the form a plus ib. So what you do is you first multiply the denominator, 3 plus 6i minus I minus 2i square. 2 plus I, 3 plus 5i plus 2. Okay. Now what you can do is you can take 5 common in the denominator. You can write this as 1/5 of 2 plus I by 1 plus I. Now since we want to write this in the form a plus ib, I multiply the numerator and denominator by 1 minus I. So ultimately what you get here is 1/5 a by 2 minus half I. You can leave it this way, or what you can do is you can multiply by 1 by 5. You get 3 by 10 minus 1 by 10 I. Okay. So this has been written in the form a plus I d. Okay. We move on to the next one, number 23. Given z1 is equal to 3 plus 5I, z2 is equal to 2 minus 3I. You need to verify that the conjugate of the quotient is equal to quotient of the conjugates. That is what you need to verify. So let's see. In fact, this is a some sort of, you can say, a proof of the property. Okay, so what you do here is you start from the left hand side. That is the quotient of the conjugate of the quotient. You first write it in the form a plus ib. You multiply the numerator and the denominator by 2 plus 3i. This, okay. So now you multiply on top. You get 6 plus 9i plus 10i plus 15i square divided by 4 square minus 9i square. So here you get 6 minus 15, which is minus 9, plus 19i divided by 16 plus 9, which is 25, and the conjugate of all this. Now you separate, you get minus 9 by 25 plus 19 by 25 times I, conjugate of this. And what do you get? minus 9 by 25 minus 19 by 25 I. So finally we remove the conjugate here in the last step. So this is our left hand side. What about the right hand side? Our right hand side is Z1 bar by Z2 bar. And what are those conjugate? What are the numbers? 3 plus 5i conjugate of this divided by 2 minus 3i, the conjugate of this. And in the numerator, what is the conjugate? 3 minus 5i. And in the denominator, what is the conjugate? 2 plus 3i. Now we again write it in the form a plus ib. Multiply 6 minus 9i minus 10i plus 15i square divided by 2 square minus 3i square, 9i square actually. So in the numerator you have 6 minus 15, which is minus 9, minus 19i divided by 4 minus 9i square, which is 13 actually, in the 4 plus 9. So minus 9 minus 19i divided by 13. Okay. So this comes to this should be 13, not 25. Here, this 2 plus 3i into 2 minus 3i, 4 plus 9, this should be 13. All this should be 13. Uh, 13. Okay, so here also you're getting minus 9 by 13 minus 19 by 13 times I. So therefore, it has been verified. Okay, so that is what this is all about, the conjugate. We now start with the modulus of a complex number. What do you mean by the modulus of a complex number? Given any complex number, modulus. Okay, given any complex number, the modulus mod of z, or also written as two vertical lines between z, mod z, is the positive square root of the real part squared plus the imaginary part squared. Okay, so therefore mod z is also written as mod of x plus iy is equal to root over of x square plus y square. So what you see is that the mod of modulus of any complex number is actually a real number. Okay, the modulus of any complex number is actually a real number always. Okay, for example, if I give you a complex number minus 1 plus 2i, therefore what should be the modulus of z? Mod z is the same as mod of minus 1 plus 2i. So now what you do is, the real part here is minus 1. So you square minus 1, add it with the square of the imaginary part. So you get root over of 1 plus 4, which is square root of 5 is the modulus of this number. Okay. So with this, we come to some of the properties. Suppose another example I can give you here before the properties. Remember, whenever you are finding out the modulus of a complex number, you will require the real part and the imaginary part separately. So if any other complex number is given to you, say a complex number that is given to you in this form, how will you find out the modulus of this complex number? How will you find out the modulus? We first write this in the form a plus ib. Okay, so what you do here is you multiply the numerator and the denominator. Six minus 4i plus 9i minus 6i square divided by 3 square minus 2i whole square. So this is 6 plus 5i plus 6 divided by 9 minus 4i square. This is 12 plus 5i divided by 9 plus 4, 13. So 12 by 13 plus 5 by 13 i. So we have separated the real and the imaginary parts of this complex number, and therefore now we are in a position to find out the modulus of z. Therefore mod z is equal to mod of 2 plus 3i by 3 plus 2i, which is the same as mod of 12 by 13 plus 5 by 13i, which is 12 by 13 square plus 5 by 13 square is equal to square root of 144 by 169 plus 25 by 169, which is equal to the square root of 169 by 169, which is square root of 1, which is 1. So modulus of this is actually 1. Okay, so this is what this was the base. These were the basic definitions of a modulus with examples. Okay, now what we want to show you here is some of the properties of modulus or absolute value. Modulus is also called the absolute value of a complex number. Okay, so properties of modulus. Yes, properties of modulus. First property, properties of modulus. Okay, first property is that if the modulus of a number, not if, that is modulus of a number is 0, then you can say that the real part of z, in fact you can say that the complex number is a zero complex number. Okay, or you can say the real part of z is equal to 0 and the imaginary part of z is also equal to 0. So if modulus is 0, you can say this, and if this is given to you, then you can say this. Okay, that is if a zero if if a zero complex number is there, then you can say obviously its modulus is 0. The next very important property is that the product of a complex number taken with its modulus is nothing but the square of the modulus. Okay, this is a very important property. The square of the complex number along or the product of the complex number with its conjugate will give you the square of the modulus. Very, very important property. Okay, and the modulus of a complex number is the same as the modulus of its conjugate. Okay, this is another property. Whether you take the complex number or its conjugate, the modulus will be the same. Okay, and number 4 is that the real part that the real part of a complex number, okay, will always lie between negative of the modulus and the positive of the modulus. Similarly, the imaginary part of this will always lie between. Okay. Now, what do you mean by this? Example. Let us say z is equal to a plus ib. So here, what is the real part? And what is the imaginary part? So therefore, and what is modulus of z? Root over of e square plus e square. Okay. So therefore, what it means is that always a will always lie between minus root a square plus b square and plus root a square plus b square. Similarly, the imaginary part will always lie between okay, this is what it means. Okay, and the next property is that the inverse, the multiplicative inverse of a complex number 1 by z or z to the power of minus 1 is the conjugate divided by the square of the modulus. Another important property, conjugate divided by the square of the modulus will give you the multiplicative inverse. In fact, if once you know the once you know the concept uh, of uh, uh, of modulus, you can find out the multiplicative inverse with the help of this result. Okay, in certain sums this will be easier to find. Okay, and you have this is again a very important property, the product of the modulus. No, in fact, the modulus of the product is equal to product of the moduli. Okay, this is another important one. And for the quotient also, you have mod z1 by z2 is equal to another important property. Mod z will be using this property for sums. These two properties will be using for sums. Okay, and triangle inequality is out of your syllabus, but was an important result from complex numbers. No longer there in the syllabus. Triangle inequality. Okay, and okay, I think that is it. Okay. So from one deduction from here is that if z1 z2 are equal complex number, if you can extend this in fact to n number of complex numbers. Okay, and from this what you can deduce is that mod of z to the power of n is equal to mod z whole to the power of n for any complex number. Okay, this deduction is important also. In fact, these two properties along with the extension and deduction are important. So please go through the properties. Next day I will work out some of the sums. Triangle inequality, please do not go through this one. This is no longer included in the syllabus. Okay, so I stop here for today.